Okay, now that we have studied single slit, the next logical thing to look at is multiple slit diffraction. So we have more than one slit, or at least two slits. Okay, in the first case, let's just look at a double slit or two slits. The difference between this double slit and the double slit we studied in the previous chapter is that in this case, the width of each slit is not all that small. Their inverse A is not that much smaller compared with lambda, so that it makes a difference whether a beam comes from the top, the middle, or the bottom of the same slit. Okay, if A is far less than the wavelengths, then you consider this beam or the middle beam or the lower beam, since they came from the same slit, they hardly make any difference in terms of phase. So I can think of this E theta 1 as a single E. Just add all the magnitudes together, have nearly the same phase, and I can do the same thing for all the beams coming from the next slit. But if A itself is comparable with wavelengths, then you have to add first beam, second beam, third beam within the same slit vectorially using phasors. Okay, so you're going to have a diffraction pattern. But then on top of that, you got E theta 1, which is the sum of all these E's, and E theta 2, which is the sum of all those E's from the second slit. These two, E theta 1 and theta 2, will have to interfere with each other. Okay, because there's a general phase difference between these two slits. So you have, on top of the diffraction pattern, you can also have an interference pattern. Okay, so that is the idea. So we call it interference/diffraction pattern for double slit. All right, the general idea is this. We're going to do it in two steps. Step number 1, we're going to add all the DEs up from the same slit. Okay, after we did that, we sum them all up. We get E theta 1 by adding all the DEs from the first slit, and E theta 2 by adding all the DEs from the second slit. And then the next step is we're going to add E theta 1 with E theta 2 to see what kind of interference we're going to get. Okay, suppose this is E theta 1, right, which is the sum of all the DEs. Basically, that will be a sinc function. Remember that? That's how we add all the all the little guys up. We get E theta 1. Okay, and E theta 2 is the sum of all the little DEs from the second slit. That's E theta 2. Now, E theta 1 and E theta 2 do not have the same phase because there is a difference in their path lengths. Okay, therefore there's a phase difference between E theta 1 and E theta 2, which is caused by what? Caused by the fact that the first slit is separated from the second slit by a distance d. Okay, that causes an angular phase difference of alpha. How is alpha calculated? Well, in the second slit, the beam has to travel an extra distance compared with the beams in the first slit. How much is that extra distance? That will be d times sine theta, right? D sine theta, just like we studied in the previous case for interference in the previous chapter. So the difference in path lengths between the first and second slit is d sine theta, and therefore you multiply this by k, you get the angular separation, the phase difference between beams from first and the second slit, and that is alpha. That alpha here, you see the phase angle between the first slit and second slit. Okay, what is the total combined electric field at the location theta? Well, we just have to add E theta 1 and E theta 2 together, and that's that. See that? Okay, that's that. Now, given E theta 1 and E theta 2 and this alpha, can we find the combined E? Yes, we can. This is a very simple exercise. We did the similar geometrical analysis in the previous chapter. Okay, first of all, assuming that these two are identical slits, they have the same width, same everything, the intensity, the brightness of the light shining upon them are the same. That tells us that E theta 1 and E theta 2 would have the same magnitude, right? They have the same magnitude. So this is an isosceles triangle, and if you then divide this, cut the base in half with this line here, this angle, as you know, is the same as that angle, and they're both equal to half of alpha. Okay, half of alpha, and therefore from here to there, I would get E theta 1 cosine alpha over 2, right? Cosine alpha over 2, and then I double it so that I can pick up not just this half, but also that half. That would give me E theta. What's E theta? E theta is the total phasor for the electric field of this combined double slit interference and diffraction at an angle theta. If I square E theta, I will get a quantity that is proportional to the intensity at the direction theta. Okay, so that is what I'm going to do. I at location theta is proportional to E theta squared, right? E theta squared. And E theta squared is right here. Okay, so that's proportional to E theta 1 squared and then cosine alpha over 2 squared. E theta 1 itself is a sinc function. Okay, don't forget it's a sinc function. What's that sinc function? It's a sinc beta over 2. Don't forget you have to square it and then times cosine squared alpha over 2. What is beta? What is alpha? The alpha is right here. What is beta? Beta, as you recall, okay, let's recall from the previous page. Beta is the phase difference between the first and the last phasor within the same slit. All right, it's Ka sine theta, right? Ka sine theta. So alpha is Kd sine theta, but beta is Ka sine theta. Writing down here again. All right. So that is I. Of course, there is a constant or proportionality which we can express in terms of the maximal intensity, which actually also happens in the middle of the screen, as you can see here. In the middle of the screen, both alpha and beta are equal to what? 0, okay? When theta, because theta is equal to 0. And interestingly enough, this is also the location where both the sinc function and the cosine function reach maximum simultaneously. All right, sinc 0, which is 1, cosine 0, which is also 1. So this whole factor becomes 1. I is equal to I naught, or I maximum. That is the central intensity in the middle of the screen. So in general, I can write I theta equals I naught, which is the intensity in the middle of the screen when theta equals 0. Sinc beta over 2 cosine alpha over 2. This whole thing squared. Okay? Now if I write out the expression for beta, the expression for alpha, I can express this more explicitly in terms of the angle theta, and I can write this. I theta equals to I naught. Okay, write down the sinc function. It is sine what? Beta over 2. It's Ka sine theta. Ka sine theta over 2 divided by Ka sine theta over 2. That is the sinc function. And then multiplied by cosine alpha over 2. Alpha is Kd sine theta. So it's Kd sine theta over 2. This whole thing squared. Okay? This is the intensity expression of a two-slit interference / diffraction pattern. Alright? Without this cosine function, all I get is a sinc function which represents the single slit diffraction pattern. But this single slit diffraction pattern is now modulated by this interference factor, cosine squared, which comes from the interference between these two slits. Okay, so if you were to plot this strange looking function, what would you get? Well, we can think about it this way. Okay, first of all, ignore the cosine function. Then you just get, just a sinc function, sinc squared, right? As we plotted before, right? But then you have to multiply this by the cosine function, which can vary between 0 and 1. Okay, so if it's 0, then despite this profile, you can get 0. If it's 1, then go all the way up to this sinc function squared. Okay, so we're going to get something like this. Let's plot it. Okay, let's plot it. We are first going to plot the profile, the sinc function squared, this general profile, without looking at the cosine function. Okay, so it is going to look like this. The sinc function, this profile, side peak, and more side peaks. Okay, side peak and more side peaks. All right, and we know what this is equal to. This is lambda over a. The argument is sine theta. Right? It's negative lambda over a and so forth. But you also have to multiply this whole thing by what? By the cosine squared function, which varies between 0 and 1. Okay, in the middle, when theta equals to 0, this is maximum. Okay, this is maximum. So you get a maximum, but then it gradually tapers down because cosine function would drop below 1 as you go away from 0. And then it's going to rise again to a maximum value, which is 1. So rise again. We can only rise up to here because that's, it's limited by this sinc function. Okay? Then it's go up and it's go down. Same thing happens on the other side. Okay? Up and down. And then it go up and down. Up and down. Up and down, and so forth. So what you see here is really an overall diffraction profile modulated by interference fringes. Okay, so these peaks are controlled by, the location of these peaks are controlled by interference, but there is an overall profile which is due to the diffraction. Okay, the overall profile depends on the width of each slit, and yet this diffraction fringe location depends on the separation between these two slits. Okay, this is in the middle. In the middle you have both maximum for interference and diffraction simultaneously, so it's a maximum. But over here, you have your first side peak for interference, not diffraction. Okay, two slit interference. What's that? That is d sine theta equals lambda, right? So this is lambda over d. Okay, and here is lambda over 2d. Right? Here is negative lambda over d. I'm sorry. Oh, that's over there. Maximum. Okay, that's right here. Now, the way I draw it, within the central diffraction peak, you have 1, 2, 3, 4, 5. You got 5 interference maxima. Okay, so on screen, what you see is this. You're gonna see this one in the middle, and there's a sideway, there's a side one, and there's another side one, another side one. This is the brightest. This is second bright. This is third bright, and that's what happens within a central peak. And away from central peak, you got something much fainter like this. You see something like that. Okay. Now you notice again, this peak is lambda over d, controlled by interference, but that minimum is lambda over a, controlled by diffraction. Okay. Since d is going to be less than a, greater than a, right? Look, d. The separation between the two slits is going to be less. It's going to be greater than a. Otherwise, the two slits will merge together, right? So it is clear that lambda over d is less than lambda over a. Therefore, you're going to have at least one side peak. Okay, at least one side peak away from the central peak, right here. How many total central peaks do we have? How many total fringes? How many total interference fringes can we have within the central diffraction peak? Well, you're going to have lambda over d, 2 lambda over d, 3 lambda over d, and so on. Actually, it's 2 lambda over d, and so on. So in general, let's say there are n maxima of interference on this side before you reach the the boundary of the central peak of diffraction. Then the angle for the nth interference maxima away from 0 would be n lambda over d. Okay, the border of the central diffraction maximum is lambda over a. Therefore, you want this thing, n lambda over d, to be less than lambda over a. Right? Has to be less than lambda over a so that it's contained within it. Alright? So what is n equal to? Lambda lambda cancels. N is less than d over a. That's how you find it. Okay? Let's say, for example, d is equal to 4.5a. So d over a is what? 4.5, right? N is an integer that's less than that. So what is the greatest possible value for n? It's going to be 4. Okay, that means you're going to have 1, 2, 3, 4. You're going to have 4 fringes here, 4 fringes on that side, of course, plus 1 in the middle. You're going to have a total of 9 fringes located within the central peak. All right, 9 fringes. Now, what if n equals d over a. So in other words, d over a happens to be an integer. If that just so happens, then what are you going to get? Well, if d is equal to 4a, for example, what does that tell you? It tells you that 4 lambda over d happens to be equal to lambda over a. So the fourth interference maximum away from 0 coincides with the first diffraction minimum. Okay, they happen in the same location. So this would have been a maximum for interference, except the diffraction is 0. So the overall intensity at that moment, which is the product of the two, of course, has to be 0. Okay, so if that happens, okay, if d over a is an integer, then we say this interference maximum is invisible, right? Because it's been, overshadowed by the diffraction minimum. I don't care whether the cosine function equals 1. The sine function goes to 0, right? So overall you get nothing. We say this interference maximum has been clipped. Okay, has been clipped. So this is a special feature when d is an integer multiple of a. Okay, we have studied single slit diffraction, and we studied two slit interference / diffraction pattern. Now we're going to move further. We're now going to study multiple slit interference and diffraction. So I don't have just two slits anymore. There are a whole bunch of them. 1, 2, 3, 4, 5, and so on. Let's, for simplicity, assume that they're each separated by the same distance d. Okay, same distance d. And so I have e theta 1, e theta 2, e theta 3, and so on. Each one of them, of course, would be a sinc function, as you know. That's the general profile and for single slit diffraction. And then you have to add all these up, e theta 1 plus e theta 2 plus e theta 3, and so on. And then the result will be interference. Okay, now let me first draw the general diffraction profile. And that, as you know, is controlled by the width of each slit, which we assume to be the same. Okay, so you have this general profile that is always the same, no matter how many slits you have, as long as each slit has the same width a. All right, and this is still lambda over a. There's still negative lambda over a. That's still the same. Okay, now the difference this time is that we have many slits that interfere with each other. If you only have two slits, then there will be an interference pattern which goes like cosine theta squared, right? Now the cosine theta squared function is not a very sharply varying function. Actually, it varies kind of slowly. Okay, so the peak, the interference peak, is actually pretty broad. If you studied Young's double slit, you know what I'm talking about. The maxima, the location of maxima, are not at all well defined. Okay, they spread out. In fact, it's easier to look at where minima are instead of maxima, because they're kind of wide. Okay, now what happens if I have a whole bunch of them? Okay, if I have a whole bunch of these slits closely spaced, okay, what I call it is what's called an optical grating or diffraction grating. A diffraction grating or an optical grating basically is made of a multiple slit pattern. Okay, there are tiny slits very closely packed to each other. A typical value would be something like 10,000 slits per inch. Okay, per inch you get 10,000 slits very close to each other. It's got a diffraction grating. The diffraction grating behaves differently from just a two-slit interference pattern. And here is how it differs. Even though we still have the same profile, which is from diffraction, which is controlled by the width of each slit, which is a. When you add more of these up, okay, things change. Now suppose at a certain angle theta, by the way, all these angles are the same. Okay, all these angles are the same. So we're looking at direction theta. When you look at a certain direction theta, let's say in this particular direction, you get constructive interference between neighboring slits. Okay, this of course happens if you have d sine theta equals n lambda, right? N lambda. D sine theta equals n lambda. So theta satisfies this particular expression. Okay, then these two are in phase, so are those two, so are those two, so are those two. So everything's in phase. Okay, This is because all these separation d's are assumed to be the same. So in this particular direction, you're going to get a bright spot. Okay, this happens when theta equals 0. Okay, this also happens when theta equals lambda over sine theta equals lambda over d, and 2 lambda over d, and so on. Okay, see, I'm marking these locations. Okay, sine theta equals 0, sine theta equals lambda over d, sine theta equals 2 lambda over d, and so on. Now, what's the difference? That looks like it's the same location for interference maxima, even for 2 slits, right? But so what is the difference then? You have a whole bunch of slits together. Well, here's the difference. Assuming if I look away from this angle, so the angle theta no longer satisfies this equation, but still it is very close to the value expressed by this. Let's say with particular values of d and lambda, you find that one direction theta, which will give you a certain maximum, is 30 degrees, let's say. So at 30 degrees, you see one of these maximum for interference. Okay. Now, what happens if you look at, instead of 30 degrees, look at 29.9 degrees? It was very close to it. Okay. As you get very close to it, if there are only 2 slits, okay, if there are only 2 slits, then these 2 slits will not exactly be in phase, but they're nearly in phase, right? Because the phase angle only differs, instead of 360 degrees, you may get, say, something like 362 degrees, but that's awfully close to 360 degrees. So these two would still be nearly in phase. So if you were to have a 2-slit interference away from that angle of maximum, the intensity is still pretty strong. So in other words, the peak, the interference peak, is kind of broad. Okay, that's what we expected. We saw a cosine theta squared. That is not a very sharp function of theta. On the other hand, when you have a whole bunch of slits, let's see what happens. Okay, let's assume that if you look slightly away from this particular angle, such that the phase difference between this guy and that guy is no longer exactly 360 degrees, but rather, let's say, 361 degrees. That doesn't sound like a big deal. But look at the next one. Next one is also 1 degree away in phase from that one compared with 360, right? So it was just 2 degrees away from that, and the next one will be 3 degrees away from the first one, and the next one will be 4 degrees, and so on. So you see, the problem here is that the phase difference adds up, okay? So as you move, 10,000 slits down, you find that the phase angles, the error keeps on accumulating. Even though the phase difference between 2 neighboring ones is not that great, away from 360, as you add a whole bunch of them, like 5,000, 10,000 of these slits, you find the phase difference simply just everywhere. Okay, what does that tell you? As you move slightly away from this angle, only slightly away, you find that the error becomes quite prominent. In other words, you're not going to satisfy coherence maximum interference anymore. So it quickly drops to 0. That is the thing. You start from maximum, but instead of a broad function, it quickly drops to 0. And same thing here. It quickly drops to 0. And quickly drops to 0. And what is the advantage of that? Better resolution. Okay? You can locate the interference maximum very sharply. And the interference maxima are controlled by this function, and the angle theta precisely because it's so well localized. And then you can find lambda precisely that way. So this is a good way of measuring the wavelengths. It's much better than only 2-slit interference, which has a much broader peak of interference for each of them.